Hey guys, tonight we drift into one of the softest, strangest questions humans have ever asked. How did time begin in the cosmos? Not just the ticking of your wall clock or the buzzing of your phone alarm, but the deep current underneath everything that changes. You know that feeling when a day goes by too fast, or a night feels impossibly long. Tonight we zoom way out, past days and years, and even galaxies, to where our best science says cosmic time itself really starts to matter. You and I are going to hover at the edge of the universe's memory and look at time not as a cold number, but as a gentle unfolding of change. And don't worry, you probably wouldn't survive being shrunk down to atom size near the beginning of the universe. But well, try it anyway, at least in your imagination. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. If you feel like sharing, tell me in the comments where you're watching from and what time it is for you right now on this tiny, spinning planet. Now, dim the lights, and let's ease into tonight's journey together. You start in a dark, quiet room. No clocks, no screen glow, just your breathing, the slow rise and fall in your chest. At first, nothing feels like it's happening. The air is still, the world is silent, and yet, if you pay attention, you notice something. Your heart thumps, your lungs stretch and relax. Somewhere, a car passes outside, a soft hum that appears and then fades. This is how time begins for you, not as numbers, but as change. One moment is not the same as the next, and your mind gently stitches those differences into a story. In that way, you're already doing what the universe does on a grand scale, keeping track of what is no longer the same. Philosophers sometimes say that time is what keeps everything from happening all at once. You can feel that in your body. Your last inhale isn't your current one. The warmth on your skin from the blanket slowly spreads, like a quiet wave. Without any clock on the wall, you still know that before and after exist, because the pattern of sensations keeps evolving. Scientists, when they get very serious about this, often start from the same simple place. Before they write equations or talk about spacetime, they talk about events, things that happen. A star ignites, an atom decays, a neuron fires in your brain as you listen to this sentence. Time, in the most basic sense, is the ordering of these events, this, then that, then something else. Imagine you're floating in a vast, black space with a single, glowing speck in front of you. The speck brightens, then dims, then brightens again. You have no watch, no calendar, no sense of how long you've been there. But you still feel a rhythm, bright, dim, bright. You can say, the dim came after the bright. Even here, stripped of everything, you've recovered a tiny thread of time. As you lie in bed, you can feel that thread inside your own mind. Memories line up behind you like faint lanterns down a road. You cannot step back into them, but you can look. Ahead of you, there are only guesses. The next thing you might do tomorrow, the way the week might unfold. Your brain, shaped by millions of years of evolution, turns raw change into a smooth mental river. Maybe the universe just loves to repeat patterns, because the same basic idea shows up in physics, time as a way to arrange change. Long before humans invented clocks, the sky was our first great timekeeper. Picture yourself standing in the chill of pre-dawn air, centuries ago. The horizon is a dark blue bruise. Stars slowly fade, birds begin their tentative chirps, and a pale glow grows in the east. You don't need to know what a second is to feel morning arriving. The transition itself, the gradual change in light, the temperature lifting a little, is enough. The earth turns, the sun seems to rise, and you, without any math, sense time moving. When science eventually did arrive with its rulers and stopwatches, it didn't erase that simple origin of time. It refined it. Physicists noticed that to study motion, how a planet orbits, how a ball falls, you always need two things, where and when. A position and a moment. But underneath those coordinates is still the basic observation that things don't stay the same. A comet's position shifts against the starry background like a slow dance. A cup of hot tea cools on your bedside table, steam curling up and fading into the room. Change is everywhere, and time is the quiet bookkeeping of those changes. If you listen closely to your own body now, you'll find several little clocks ticking inside. Your heartbeat has its own rhythm. Your breathing settles into a slower pattern as you relax. Even your body temperature follows a daily cycle, warmer at some times, cooler at others. Your cells divide, repair, and age. Without any digital display, you are a living calendar of tiny transformations. At the scale of the cosmos, something similar happens. Clouds of gas collapse into stars, stars burn, fuse elements in their cores, and eventually die, spreading heavy atoms that will one day make planets, oceans, and the calcium in your bones. Astronomers track these life cycles, not by looking at a single star through its whole story that would take billions of your years, but by looking at many stars at different stages, like pages torn from different chapters of the same cosmic novel. When they line those pages up, they see an arrow pointing from simpler, smoother beginnings to more complex, structured scenes. Again, it's all about change, arranged in order. As you think about how time began in the cosmos, it helps to remember that, for science, the story starts with what can be measured. We can measure the expansion of the universe, the cooling of its background radiation, the ages of stars. From that, we reconstruct a history, a hotter, denser, early universe, slowly spreading out and thinning. In that history, time is the parameter that tells us how far along the story we are from the fiery youth of the cosmos to the quieter, star-sprinkled era you inhabit now. But lying here, maybe with your eyes heavy, you also feel another layer. Time isn't just outside you, it's inside your experience. Some minutes feel thick and heavy, some hours slip away like water. Your internal sense of change doesn't always match the precise beats of a clock. A 5-minute meditation can feel like a small eternity of stillness. An hour of laughing with friends can vanish in what feels like a heartbeat. The universe runs on its own steady laws, but your mind paints time with emotion and meaning. That's where this journey begins, at the meeting point between cosmic change and personal change. Before we talk about equations, or the Big Bang, or quantum beginnings, we start with that simple, noticing you're doing right now. Breath in, breath out. One word finishes, another begins. Your thoughts slowly quiet down. Time, in this soft, human sense, begins whenever something is different from what it was just a moment ago, and you are there to witness it. In the sections ahead, well, stretch this idea outward until your quiet room connects all the way back to the earliest instance of the universe. For now, feel the weight of the blanket, the cool or warm air around your face, the gentle unfolding of this moment into the next. Somewhere, galaxies are turning, stars are being born and dying, and here you are, a small conscious ripple in that enormous sea of change, listening to the story of how time itself might have begun. You're still lying there in the half-dark, listening, when the question shifts slightly. It's no longer just, what does time feel like to you, but what does time mean to a physicist? You can almost imagine some quiet scientist at a blackboard, chalk dust on their sleeves, thinking about the same invisible flow that you feel in your chest right now. In everyday life, time feels personal. It stretches during a boring meeting, compresses during a beautiful sunset. But if you ask a physicist what time is, they'll usually start with something much more stripped down, almost austere. Time is what clocks measure. It sounds disappointingly simple at first, almost like a joke. Yet, in that simple statement is a powerful idea. Instead of arguing about the essence of time, you focus on how to compare earlier and later in a reliable, repeatable way. Imagine holding a small, perfectly designed clock in your hand. Its ticking is steady, like soft raindrops on a roof. Every tick marks 1 second. If you watch a ball roll across the floor, you can say, it started moving at this tick and stopped at that tick. The difference between those readings is what we call a duration. To a physicist, that duration measured by a standardized clock is time in one of its cleanest forms. You can picture the universe as a vast archive of events, stars exploding, atoms colliding, you blinking slowly in your room. Physicists label these events not just by where they happen in space, but when they happen in time. One way to imagine it is as a kind of invisible grid, with 3 directions for space: left, right, up, down, forward, back, and 1 extra axis that runs from past to future. Every event occupies a unique address on this 4-dimensional map. Your current position is not just on your bed, but on your bed at this particular moment. That's one of the quiet revolutions of modern physics, treating time as a coordinate, just like the coordinates of space, but with its own special role. The world isn't a sequence of separate frames, like still photos in a stack. It's a smooth, four-dimensional fabric where your entire life can be traced as a line, a world line, threading from your birth to this very moment and onward into the unknown stretches of your future. As you exhale, you can imagine that line of your world line gently curving forward, each heartbeat another point on its path. The room around you becomes part of a larger diagram in your mind. The walls, the ceiling, the stars above it all, each with their own lines woven together in this four-dimensional tapestry. Maybe the universe just loves to repeat patterns, because the same idea applies to planets orbiting a star, photons flying through space, or a falling leaf outside your window. Each has its own world line, its own trail through space-time. Before Einstein, physicists like Newton thought of time as a universal river that flowed the same way for everyone, everywhere. In that view, you could imagine a giant, cosmic clock ticking in the background, keeping perfect time for the whole universe. Differences in motion didn't matter. Everyone agreed on the same now. It's a comforting image, like a single, massive heartbeat that unites everything. But when experiments began to probe the speed of light and the behavior of moving clocks, cracks appeared in that picture. Physicists found that different observers, moving relative to each other, did not agree on how long certain processes took. A clock on a fast-moving spaceship might genuinely tick more slowly than a clock resting on your bedside table. And yet, both clocks are working perfectly, following the same physical laws. You can imagine this by thinking of two identical metronomes. One sits beside you, clicking softly. The other is placed on a train that whips past at an incredible speed. From your vantage point, if you could somehow see its ticking, you'd find that the train's metronome runs a little slower than yours. Time, it seems, is no longer a single, rigid, marching beat. It depends on how you move. In Einstein's special relativity, time and space fuse into space-time, and time becomes a flexible coordinate that can stretch or shrink depending on your motion. Yet, for each individual object or person, there is still something steady, the time recorded by a clock that travels with them, which physicists call proper time. Your proper time is what your own heart, your own cells, your own wristwatch would measure as you wander through the universe. On that internal clock, your life always feels normal. It's only when you compare with someone else who has taken a different path through space-time that the differences emerge. As you listen, you might picture astronauts on the International Space Station. They orbit Earth at high speed, and though the effect is tiny, their proper time moves a little differently from yours. When they return, their internal clocks and their precise instruments have experienced slightly less time than people on the ground. It's as if their world lines through space-time were just a little shorter between the same start and end events. In this way, physicists treat time as both humble and profound. On the one hand, it's simply a parameter in equations, the t that lets you write down how a planet moves or how a wave oscillates. On the other hand, that t takes on a new life when you realize it is part of a four-dimensional geometry, and that its structure can bend, warp, and differ from observer to observer. Even the idea of a moment gets refined. In your experience, a moment is the thickness of your awareness, the feel of sheets against your skin, the quiet hum in your ears, the weight of your eyelids. In relativity, a moment for you is a slice through space-time that is all the events you call now. For someone flying past you at high speed, that slice tilts. There now includes events that, for you, are partly in the future or the past. It's a bit like two people cutting a cake at different angles. The slices overlap in some places, but not in others. That sounds abstract, but you don't need to picture the full diagrams to feel the essence of it. Just imagine that the universe does not come with a single, absolute clock stamped into its fabric. Instead, every path, every motion, every world line carries its own rhythm. Time, to a physicist, is the way these rhythms are measured, compared, and interwoven. As you lie here, you are both a soft biological clock and a tiny traveller through space-time. Your heart and your thoughts keep a steady count of your proper time, while the Earth spins and orbits the Sun, carrying you along a much larger arc. The galaxies beyond drift, collide, and reshape, each with their own long, slow tempo. The physicist's definition of time, part coordinate, part duration, acts like a quiet scaffolding that holds all these motions together in a single, coherent story. Maybe, as your breathing slows, you can appreciate how delicate this idea is. Time is not just a feeling, and not just a number on a clock face. It is the structure within which change becomes describable, where cause leads to effect, where your childhood memories sit safely behind you on your world line, and your possible futures branch gently ahead. The equations that physicists write are like musical scores, and time is their staff, the baseline along which notes unfold. For now, you don't need to solve anything or remember any terms. Just know that, in the language of physics, time is the measured separation between events, woven with space into a single fabric. You are resting inside that fabric, weightless, being carried along your own world line while the cosmos writes its slow, patient symphony around you. You're still drifting in that four-dimensional picture, where your life is a line through space-time, when the scene slowly zooms out. The grid you imagined 3 directions of space and 1 of time starts to feel less like a rigid scaffolding and more like something softer, something that can bend and ripple. You picture yourself floating far above Earth, in the quiet dark. Below you, the planet glows in blues and nighttime yellows, wrapped in a thin halo of atmosphere. There's no sound, only the faint hum of your own breath inside an imaginary spacesuit. Out here, the idea of down is already strange. You're not standing on anything. You're simply following a path through space-time. And this is where Einstein's big leap arrives. What you've always called gravity is really the shape of that path. In his general theory of relativity, Einstein suggests that space and time together form a fabric space-time, and that this fabric is not stiff. Massive objects like Earth, the Sun, or a black hole dent and curve it. You might have seen the classic image, a bowling ball sitting on a stretchy rubber sheet, making a dip, while smaller marbles roll around the indentation. It's not perfect, but as a bedtime picture, it works. The marbles aren't being pulled by an invisible force, they're just following the natural curves in the sheet. Now translate that into your floating experience. You and the Earth are both tracing out world lines, natural paths through space-time. The Earth's mass curves the fabric around it, and if you let yourself drift in free fall, say, in orbit, you feel weightless, even though gravity is still there. You and the International Space Station are like marbles gliding around that dip in the rubber sheet, never needing a push, simply following the shape. You close your eyes and feel what that might be like. Your stomach is light, your limbs drift, your body no longer pressed against mattress or floor. Inside your suit, there's a coolness on your face, a gentle pressure of air. Outside, the Earth silently slides beneath you, oceans turning like slow, dark ink. In this curved space-time, your world line is the straightest possible path, even though, from far away, it looks like you're circling the planet. Jerez, the part that connects back to time. In general relativity, when space-time curves, time does too. Clocks don't tick at the same rate everywhere. Down near the surface of Earth, deeper in that curvature, time passes just a little more slowly than it does for someone farther away. Not enough for you to feel in your body, but enough that precise experiments with atomic clocks have measured it. The fabric of time itself stretches and compresses depending on where you are and how fast you're moving. Imagine holding 2 identical, glowing clocks. One hovers with you high above the Earth. The other sinks down toward a massive planet, or closer to the invisible edge of a black hole. In your mind's eye, you watch them tick. The clock nearer the mass blinks just a bit more slowly, its light pulses lagging behind. To that clock, everything feels normal. It never senses anything strange, but when you compare them, you see that the lower clock's time has dilated, stretched out. You can translate that into a more grounded image. Think of a deep, soft mattress. When you lie in the middle, your body settles into a dip. A friend sits near the edge, where the mattress is higher and flatter. If you both roll a marble in a straight line, yours curves inward more dramatically, following the deeper contour. In space-time, something similar happens to both space and time near massive objects. The geometry is changed, and the straight paths, including the paths of clocks, adjust. Einstein's field equations, the heart of his theory, are like a quiet conversation between spacetime and matter. Matter tells spacetime how to curve. Spacetime tells matter how to move. Those equations don't just describe planets and apples. They describe the expansion of the entire universe, the creation of black holes, the bending of light from distant galaxies. They're the mathematical poem that underlies your whole cosmic setting. As you lie in bed, you are actually sitting inside one of those solutions to Einstein's equations. A universe that is, on large scales, expanding, with galaxies receding from each other like dots on a stretching balloon. Time in this cosmos is not just a simple line, it's a dimension woven into a dynamic, evolving fabric. The beginning of time becomes, in this language, the earliest stage where this fabric can meaningfully be described. Maybe the universe just loves to repeat patterns, because the idea of curvature shows up in smaller ways too. You know what it feels like when a road bends, your body gently leans as the car follows the curve. In space-time, the bending is invisible to your eyes, but your body still obeys it. When you jump off a high ledge and feel your stomach swoop, you are briefly in free fall, following a geodesic, a natural path in curved space-time, until the ground stops you. Your sensation of weight is not because gravity pulls you down, but because the floor continually shoves you away from your preferred falling path. There's a softer way to feel this in your imagination. Picture a beam of starlight passing near the Sunday. In the old view, light should sail straight by, unbothered by gravity. In Einstein's view, the sun curves space-time, and light follows that curve. The path of the star's light bends, and from Earth the star appears slightly shifted from its true position. Astronomers have measured this, watching starlight slide fractionally aside during solar eclipses. You can imagine those beams as thin, shimmering threads being gently steered by the sun's invisible well. All of this bends back toward our central question. How did time begin in such a universe? If time is part of a fabric that curves and stretches, then to ask about its beginning is to ask about the earliest shape of that fabric. Was there a moment when the fabric itself emerged from some deeper, possibly timeless reality? Or did the fabric exist in some other form before what we call the Big Bang, a word that might not capture the subtlety of space-time's own birth? For now, you don't need to answer. You just rest inside the idea that time and space are not separate things, but different faces of one geometry. Your life, your memories, every heartbeat, every orbit of Earth around the sun, they all trace lines and curves in this shared fabric. When you look up at the night sky, you're not just seeing objects scattered in a black void. You're looking into the warped, dynamic stage on which the universe's story unfolds. As your breathing slows, let the complexity fade into a simple image. A vast, dark, flexible sheet, sprinkled with glowing marbles. Wherever a marble sits, the sheet dips. Smaller marbles roll along the curves. Tiny lights blink slowly or quickly depending on how deep they are in the dimples. You are one of those lights, carried along, your time entwined with the bending of the sheet itself. Somewhere in that fabric, at what we call the beginning, the curves become extreme, and our current equations start to tremble. In the next part of our journey, start gently rewinding the cosmic story, following those curves back toward that mysterious edge where space-time and time itself comes to its earliest known form. For now, just feel yourself cradled in the fabric, supported by a universe that quietly shapes the passage of every second you experience. You're lying there, nested in the curved fabric of space-time, when a quiet thought arrives. If the universe is expanding now, what happens if you run the story backwards? Not just in your head, but in the language of physics itself. You can imagine a giant, cosmic remote control in your hand. Right now, it's on play. Galaxies drift apart, stars burn their fuel, planets spin and cool. You feel time as a steady slide from earlier to later, but in your imagination, you slowly press rewind. The first thing to rewind is the expansion. Astronomers have measured that distant galaxies are, on average, moving away from us. Their light is stretched into redder colors, like a siren's pitch dropping as it speeds away. This redshift is one of the key signs that space itself is stretching. So in your mind, you take that stretching and gently reverse it. The galaxies begin to creep closer. Their redshift shrinks. The universe, on the largest scales, starts to contract. To picture it, think of a balloon with dots drawn on its surface. When the balloon inflates, every dot moves away from every other. Now imagine slowly letting the air out. The dots drift back closer together. The surface wrinkles a little. In your room, you can almost feel a faint pressure change, like a soft breeze collapsing inward instead of flowing outward. That's your mind's way of turning the universe's expansion into a tactile sensation. In real cosmology, this rewind is more than a metaphor. When scientists plug what we see galaxy redshifts, the density of matter and energy, into Einstein's equations, they get the Friedmann equations, which describe how the size of the universe changes over time. These equations are time-symmetric in a mathematical sense. If you change the sign of time, they still make sense. In other words, if an expanding universe is allowed by the equations, a contracting one is, too. So you keep rewinding. Galaxies that were far apart now move closer together. Clusters merge into brighter, denser knots. The sky, if you could watch it on fast reverse, would turn from a sparse sprinkle of light into a crowded blaze. The spaces between galaxies shrink. The average density of the universe rises. Instead of cold and thin, the cosmic gas grows thicker and hotter. You can imagine the background glow of the cosmos today, a faint microwave whisper slowly intensifying as you go back. It warms from microwaves to radio waves, to infrared, to visible light, until the whole sky becomes a uniform, bright fog. It's like someone slowly turning up a cosmic dimmer switch, washing out individual stars and galaxies until all you see is an overwhelming, even brightness. Along this rewinding, you pass milestones that cosmologists map out. Galaxies unforming as stars fall back into dense gas, stars themselves defusing, unmaking heavy elements into lighter nuclei, atoms breaking apart into charged particles, nuclei dissolving into a plasma of protons, neutrons, and electrons. Each step backward is a step towards simplicity and extreme conditions. Your mind can almost taste the heat, a dry, searing intensity that makes the air in your room feel cool and gentle by contrast. Maybe the universe just loves to repeat patterns, because this backwards journey mirrors, in reverse, the story of cosmic evolution we think actually played forward, from smooth, hot, dense beginnings to clumpy, cool, structured spacetime. The equations that describe this are neat and symmetric, like a reversible recipe. If you know the ingredients and the rules, you can run them either way. But as you float through this mental rewind, you might feel a tension. In everyday life, you never see a shattered glass leap back together or smoke return to a candle. Your memories, your aging, the cooling of your tea, these all run one way. Yet in many of the basic laws of physics, including Einstein's equations, there's nothing that forbids running the tape backwards. How can both be true? For now, just notice that contrast. At the level of fundamental interactions, many processes look the same whether you move forward or backward in time. A movie of two ideal billiard balls colliding can be played in reverse, and you'd have trouble telling which version is the real one. But when you zoom out to the messy complexity of everyday life, you can almost always tell. Rewinding your whole day would look obviously wrong. Food uncooking, conversations unhappening, the sun rising in the west. In the universe scale rewind you're imagining, you're mostly following the clean, large-scale behavior described by cosmological equations. You're ignoring, for the moment, all the local messiness, the entropy and randomness, the smeared frosting of complexity on top of the basic expansion. In that smoothed-out picture, the universe behaves like a simple, reversible system. Its overall size shrinks symmetrically as you step back in time, and so you continue. The cosmic temperature climbs. On your internal dial, you watch it rise from a few degrees above absolute zero today, to thousands, then millions, then billions of degrees. Particles race around at near-light speeds, constantly colliding, the distinction between matter and radiation blurring. If you try to imagine standing there, you can't. There are no atoms to form your body, no stable structures for you to inhabit. You are, at best, a ghostly observer, watching a blazing, featureless soup. Eventually, as you rewind far enough, you approach an extreme limit where the density and curvature become enormous. The scale factor, the measure of the universe's size in those equations, shrinks towards zero. This is what, in our current mathematical description, looks like a singularity, a point where the temperature and density go to infinity, and our equations cease to give sensible answers. Here, your cosmic remote starts to shake in your hand. The rewind button trembles, because the story, as written in classical general relativity, simply stops. It's like running into the edge of a map labelled, "Here be dragons." The equations tell you that if you take the smooth fabric of space-time and run it back far enough, it crumples into a state that the theory itself can't handle. The coordinates go haywire. Curvature blows up. Time, as defined by those equations, reaches a boundary. Lying in your bed, you might picture this as the fabric we spoke about earlier, being stretched tighter and tighter as you go back, until the threads are pulled so taut that the weave itself begins to break down. The sheet is no longer a smooth surface. It's fraying into something more primitive, something the current loom of physics cannot yet describe. And this, in the language of modern cosmology, is close to what we call the Big Bang. Not a conventional explosion in space, but the moment when the entire observable universe was in an extremely hot, dense state, and then began to expand. When we say time began at the Big Bang, what we often mean is that, within the framework of general relativity, the concept of earlier times becomes undefined. The equations don't safely carry us beyond that limit. You might feel a flicker of discomfort at that idea, a beginning beyond which our usual notion of before loses its footing. But it can also be comforting. It means that when you run the universe backwards with your mind, you are not expected to have all the answers. Even our best theories hit a kind of horizon. For tonight, you can rest with this picture. The cosmos as a movie that, according to our best large-scale equations, could be run backward from its current expansion into a denser, hotter, simpler past until you reach an edge where that mathematical film burns out. On one side of that edge, we have rich, detailed frames. On the other side, we have questions. As your eyes grow heavy, feel the strange, gentle power of that. You live in a universe whose story, as far as we can tell, can be traced back through billions of years of change, guided by equations that are eerily reversible up to a point. You don't need to solve them. You just need to know that your quiet breathing now is part of a vast narrative that, when run in reverse, leads not into nothingness, but into the frontier where new physics waits to be discovered. You're still holding that trembling cosmic remote, the universe flickering in reverse. When the frames finally slow down, the galaxies, which were rushing inward, now blur into one another. Stars dissolve back into incandescent gas. The bright fog thickens until it's no longer a fog at all, but a blinding, uniform radiance. You pause the tape at the moment cosmologists mean when they talk about the Big Bang. Right away, it helps to soften one common picture. This is not a bomb exploding into empty space, with fragments flying into a pre-existing void. Instead, everything you know as space is already part of the event. Space itself is compressed into an unimaginably hot, dense state, and then begins to expand. There is no outside for the universe to explode into. The expansion happens everywhere at once. You can imagine shrinking your room. The Earth, the galaxy, everything down together. The walls draw closer. Your bed compresses. The distances between every atom in your body and every star in the sky squeeze down in a coordinated, almost musical way. If there were a soundtrack, it might be a deep, rising hum, like the build-up before an orchestra erupts into sound. The temperature climbs sharply. Matter and radiation blur into a seething, glowing plasma. In the language of cosmology, we describe this using a cosmic time, a kind of universal clock that starts counting from this very hot, dense state. On that clock, the moment you're paused at is not nothing. It's a specific, finite, though extreme, state of the universe. Incredibly small, incredibly hot, incredibly uniform. The density is so high that ordinary matter cannot exist in its familiar forms. There are no atoms, no molecules, no stable structures, just particles and fields in a furious, energetic dance. As you hover here, your imagination tries to give this state a texture. You might picture it as a white gold mist so bright it hurts, pressing against you from every side, with no over there to escape to. The concept of distance loses its usual meaning. Anywhere you try to point is also right here, because the whole observable universe fits into a volume you could never truly visualize. The heat is beyond any furnace, any star's core. It makes the hottest flame you've ever seen feel like a cool candle beside a star. Cosmologists reconstruct this moment, not from photographs, but from the footprints it leaves behind. The expansion of galaxies tells us the universe is stretching now. When we wind that back, we get higher densities in the past. The cosmic microwave background, the faint afterglow we'll meet more deeply later, tells us that around 380,000 years after this hot start, the universe was still a nearly uniform bath of radiation at thousands of degrees. The abundances of light elements like hydrogen, helium, and lithium match what you'd expect if, in the first minutes after this moment, the cosmos was dense and hot enough for nuclear reactions to briefly ignite, forging those elements before cooling. Put together, these clues form a coherent story. There was indeed a time when the observable universe was in a state that's small, hot, and dense by any human standard. That's what we call the Big Bang. Not a firecracker, but the initial condition from which the cosmic movie begins, as far back as our current classical equations can reliably reach. Maybe the universe just loves to repeat patterns, because this Big Bang state echoes something you've already felt in smaller ways. Think of heating a pot of water. At first, you see calm stillness, then tiny ripples appear, then vigorous bubbling. At very high heat, the water becomes chaotic, steam violently rising. If you reverse time in your head, all that froth collapses back into smooth stillness. The Big Bang is like that reverse in the extreme. All the scattered, cool, structured complexity of today's universe folded back into a smooth, intense beginning. You might wonder, if this is the beginning of time, what does before mean? On the cosmic clock defined within general relativity, time is measured from this hot state onward. The equations give you a scale factor, a number that tells you how big the universe is at each moment. As you rewind, the scale factor shrinks, approaching zero at a finite time in the past. That moment of zero size, infinite density, and infinite curvature is what the math calls a singularity. But a singularity isn't a physical thing you could visit. It's more like a signpost saying, our current theory no longer applies here. General relativity, the same theory that so beautifully described curved spacetime and expanding universes in the last sections, begins to break down when densities approach the so-called Planck scale. Quantum effects, those strange, shimmering rules that govern particles at very small scales, can no longer be ignored. The fabric of spacetime itself might become quantized, grainy, or fluctuating in ways we don't yet fully understand. So when people say time began at the Big Bang, they often mean, within the framework of classical general relativity, this hot, dense state is as far back as time is defined. Asking what happened before is like asking what's north of the North Pole. The coordinate system itself stops there. But that doesn't necessarily mean there was literally nothing, or that no deeper description exists. It just means we've hit the boundary of our current map. Lying in bed, you can let this be less of a sharp edge and more of a gentle mist. On one side, the side you live on, the universe expands, cools, and structures form. Galaxies, stars, planets, you. On the other side, instead of a clear picture, there is uncertainty. Perhaps a quantum foam, or a previous cosmic phase, or some timeless structure from which time itself emerges. Well, tiptoe closer to that in the next section. For now, it's enough to recognize that the Big Bang moment marks the beginning of the cosmic time we can speak about with our present laws. As you listen, perhaps your own life feels small in comparison to a universe that is 13.8 billion years old. But notice something gentle in this perspective. The same mathematics that traces the universe back to its hot beginning also governs the fall of an apple, the orbit of the moon, the way GPS satellites correct for time dilation so your maps work. The Big Bang is not just a distant, exotic event. It's the earliest chapter of the same story that shapes your commute, your night sky, your heartbeat. In your imagination, let's stand right at that threshold. Behind you, in the direction of later, lies everything familiar. Cosmic microwave background, galaxies forming, stars lighting up, Earth coalescing, life evolving. your ancestors looking up in wonder. Ahead of you, in the direction of earlier, lies a fog of theoretical possibilities. Between them sits this luminous, intense state that our equations point to and our observations support. Maybe, in a quiet way, this is what beginnings often are. Not perfectly sharp moments, but thresholds where one kind of description gives way to another. The Big Bang, as we currently understand it, is such a threshold. It's the earliest place where the fabric of space-time can be treated as smooth, where the idea of a cosmic time coordinate becomes meaningful, and where we can trace the unfolding of change with confidence. As your eyelids grow heavier, you can imagine the Big Bang not as a violent blast, but as a single, bright note that starts a very long, very slow symphony. The note is too intense for life, for atoms, for anything familiar, but as it echoes and expands, the music it contains gradually separates into harmonies. Particles, atoms, stars, galaxies, minds. You are listening, right now, from very far along in that melody. In the next part of our journey, we'll zoom in even closer to the first instance after this bright beginning, to a timescale so tiny it almost slips between your thoughts. The Planck time, where quantum gravity whispers at the edge of what we can know. For tonight, rest with the knowledge that your entire life unfolds many, many verses into a song that, as far as we can tell, began with a single, radiant chord we call the Big Bang. You're standing at the threshold of the Big Bang's bright beginning, the universe around you a furious, uniform blaze. Now, we're going to do something even stranger. Not just rewind the cosmic movie, but zoom in on its very first frames. So far in that each frame is almost no time at all. Imagine the universe has just started to expand from that hot, dense state we talked about. Cosmologists often describe what happens in the first second, the first minute, the first 1,000 years. But there's a much, much smaller slice of time that plays a special role, the Planck time. It's about 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 That's 5.39 times 10 to the minus 44 seconds. Your mind can't really hold that number, and that's okay. It's less a length of time you feel, and that's okay. It's less a length of time you feel, and more a border drawn by nature's constants themselves. To find the Planck time, physicists combine three fundamental pieces: the speed of light, which sets how fast anything can move; Planck's constant, which underlies the graininess of quantum mechanics; and Newton's gravitational constant, which tells you the strength of gravity. When you put these three together in just the right way, you get a natural unit of time, built not by humans, but by the universe's own rules. That unit is the Planck time. In a sense, it's the timescale at which both quantum effects and gravity are equally important. You can think of it like this. For times much longer than the Planck time, you can usually treat space-time as a smooth fabric, the way Einstein did. Gravity curves it, but the fabric itself is continuous. Quantum effects mostly show up in particles and fields living on that fabric, not in the fabric's own structure. But as you push back toward the Big Bang, squeezing more and more energy into smaller and smaller regions, the smoothness starts to wobble. At around the Planck time after the Big Bang, the density and curvature are so extreme that the fabric itself may begin to behave in quantum, jittery ways. Close your eyes and imagine space-time not as a calm, stretched sheet, but as something like the surface of a boiling pot, only far more subtle and fine-grained. Tiny ripples flicker everywhere, appearing and vanishing so quickly you can barely say they existed. Distances blur. The notion of a clean, straight line between two events becomes fuzzy. The universe isn't yet the quiet, continuous canvas we like to sketch on. It's more like a shimmering, pixelated mist of possibilities. In that mist, the usual idea of before and after begins to lose its grip. Our familiar time, the one you feel in your heartbeat and see on your phone, is built on space-time being smooth enough for clocks to behave predictably. But in the Planck era, right around the Planck time, those clocks, if they could exist, would be overwhelmed. Gravity would be so strong, and quantum fluctuations so wild that the tick of any imagined clock would smear into uncertainty. Maybe the universe just loves to repeat patterns, because this reminds you of everyday situations where your categories fall apart at extremes. Think about trying to describe water at the exact moment it's turning into steam on a hot pan. Is it liquid? Is it gas? It's both and neither for a brief transition. The Planck time is like that. But for spacetime itself, a transition region where the classical idea of a smooth geometry melts into something we don't yet fully know. Lying in bed, you can try to give this era a sensory feel. Instead of a gentle, continuous flow of seconds, picture time as a rapid flicker, like a strobe light flashing so fast that individual flashes blur into a steady glow. The air around you seems to quiver in sync with some ultrafast pulse. You can't separate one shimmer from the next. They merge into a single vibrating presence. That's one way to imagine the early universe near the Planck time. Not a calm, continuous river of time, but a torrent of quantum foam, where even the riverbed is dissolving. This is the domain of what physicists call quantum gravity, a theory we don't fully have yet. General relativity tells us how space-time curves, but treats it as smooth and classical. Quantum mechanics tells us how particles and fields behave in a fundamentally grainy, uncertain way, but usually assumes space-time is a fixed background. At the Planck scale, these two pictures collide. You can't ignore gravity, and you can't ignore quantum effects. You need a unified description. Some researchers explore loop quantum gravity, where space-time itself is made of tiny, discrete loops, like an invisible chainmail. Others work with string theory, where the fundamental constituents of reality are tiny vibrating strings, and space-time emerges from the way these strings interact. There are spin foams, causal sets, and other approaches, each a different way of trying to sketch what space-time looks like when you zoom in so far that the smooth fabric from earlier sections is revealed to be woven from something more elementary. You don't need to follow the mathematics to feel the philosophical shift. Earlier, time was part of a continuous coordinate grid. It was a dimension where events could be neatly ordered, cause preceding effect. Now, you're being told that at some extreme, early moment around the Planck time that neat picture may not apply. Instead of a well-defined timeline with a clear zero, you have a hazy region where our standard concepts falter. This is why cosmologists often say, our story of the universe is reliable back to a fraction of a second after the Big Bang, and speculative beyond that. That fraction is enormous compared to the Planck time. From about 10:43 seconds onward, we can start to talk about processes like inflation, particle production, nucleosynthesis, and so on, using a mixture of general relativity and quantum field theory. But right at the Planck time and before, we lack a tested theory. The universe's first breath is, for now, exhaled in a language we don't fully speak. Still, you can let this uncertainty be calming rather than unsettling. The fact that our equations stop being trustworthy, there is not a failure. It's a sign that we've reached the edge of currently mapped knowledge. Just as sailors once drew dragons on the edges of their charts, physicists draw symbols Ha, C, G, combining them into Planck units and saying, here is where something new begins. You might reflect that your own life has moments like this, times when the normal rules you live by no longer make sense, a sudden loss, a big change, a threshold experience. Before and after feel real. But the moment itself is blurry, a kind of internal Planck time where your usual definitions tremble. The universe, on its grand scale, seems to carry a similar signature, a region where the familiar idea of time is not yet born, but something is already happening. In the image of our cosmic journey, the Planck time is like the first exhale after that bright initial chord of the Big Bang. It's the earliest whisper where space-time begins to behave enough like a continuous fabric that we can even talk about moments at all. Before that, if before even applies, the story might be written in an entirely different grammar, timeless equations, quantum states without a conventional clock, or a bounce from a previous cosmic era. Well, explore some of those possibilities soon. For tonight, let your thoughts drift back to your room. The sheets brush your skin with a soft, steady texture. Your breath flows in and out at a human timescale, seconds long, comforting and familiar. Your heart ticks out its own rhythm, thousands of times longer than the Planck time, and yet connected to it because all timescales in the universe, from the smallest to the largest, share the same underlying constants. As you feel your body grow heavier into the mattress, you can picture those constants, C, G, and H, like quiet, invisible guardians of reality. From their interplay comes the Planck time, that earliest threshold, the first breath of cosmic time, as we can meaningfully describe it. Everything you are, everything you remember, unfolds on a stage that has been expanding since that barely there instant. Somewhere, in the silence beneath your awareness, the universe still carries the imprint of those first, quantum trembling moments. You don't need to see them. It's enough to know that your story rides on waves that began at a scale so small, so brief, that it is almost more like a question than an answer. You're hovering now just beyond that ghostly Planck era, where space-time was too jittery to fully trust. As you drift a little later on, the cosmic clock, fractions of a second, but unimaginably rich ones, the universe begins to calm, just enough for something remarkable to happen. The fabric of space-time, still incredibly curved and energetic, settles into a phase many cosmologists call inflation, a period where space itself expands at a staggering, almost unbelievable rate. Distances double and double again, over and over, faster than you can whisper the word now. If you try to imagine it, think of a tiny dot of ink on a balloon. In an instant, the balloon swells so quickly that the dot is pulled into a long, thin smear. In your room, you might feel this as a sudden, silent stretching of everything, like your sheets and the walls briefly trying to rush away from each other, too fast for sound to keep up. But the star of this section isn't just the expansion. It's the tiny, restless tremble that rides on top of it, quantum fluctuations. In quantum physics, emptiness is never truly empty. Even in what we'd call a vacuum, fields are there, humming faintly with energy, constantly producing and annihilating pairs of particles in brief, almost imaginary flickers. This restless activity is a consequence of the Heisenberg uncertainty principle. If you try to pin down the energy of a region perfectly, you lose all certainty about when and how that energy appears. So the vacuum cheats a little, borrowing energy for a short time to create virtual particles, then paying it back just as quickly. Now picture that kind of jitter happening in the very early universe, in the field or fields, driving inflation itself. Tiny quantum fluctuations, little bumps of slightly higher or lower energy flicker into existence everywhere. They're microscopic beyond your imagination. Under normal circumstances, they would remain that way, invisible blips in the fabric of reality. But these are not normal circumstances. The universe is inflating. As space balloons outward at tremendous speed, it stretches those quantum ripples like taffy. What began as a tiny fluctuation, maybe smaller than a proton, gets pulled across distances that will one day be light years wide. It's as if you blew on a pan of simmering water, and small ripples froze into enormous, slow-moving swells. The rapid expansion of space freezes in these fluctuations, turning what would have been fleeting whispers into permanent features of the cosmic landscape. You can give this a sensory shape. Imagine holding a still bowl of water lit by moonlight. Tiny, random ripples dance on the surface, here one moment, gone the next. Now, imagine that, in an instant, the bowl grows to the size of a lake. Those once small ripples are now vast, gentle waves rolling under your boat. Inflation does something like that to the quantum fluctuations of the early universe. It promotes them from microscopic jitters to macroscopic patterns. These patterns become seeds of structure. In some regions, the stretched quantum fluctuations leave slightly more energy, slightly more matter. In others, slightly less. Over billions of years, gravity amplifies these differences. Places with a bit more matter pull in even more, eventually forming galaxies, clusters, and vast cosmic filaments. Places with a bit less become the great voids between. Maybe the universe just loves to repeat patterns, because you've seen this theme before in your own life. Tiny differences, tiny fluctuations at the beginning of something, growing into big consequences later. A chance meeting, a small decision, a slightly different mood one morning, these can bloom into entire new branches of your personal story. The cosmos seems to run on a similar principle, turning small quantum randomness into the grand architecture of the night sky. We have evidence of this process frozen in light itself. When you look through the eyes of satellites and telescopes at the cosmic microwave background, you see not a perfectly smooth glow, but a pattern of tiny temperature differences, 1 part in 100,000. These faint, mottled patches are like a baby picture of the universe, taken when it was about 380,000 years old. The patterns match what you'd expect if inflation took quantum fluctuations and stretched them into density variations. In that faint, speckled light, you're literally seeing the fingerprint of quantum jitters from the earliest instants. As you lie in the dark, imagine the air around you shimmer with a delicate speckle pattern, warmer here, cooler there, by just a whisper of a degree. You run your hand through it and feel almost no difference. And yet, given enough time and gravity, those slight variations could grow into stars and galaxies. The fact that you exist, here and now, listening to this story, is tied to those original speckles, those ancient quantum fluctuations amplified by inflation. So where does before come into this? In a quantum world, the idea of a single, sharp history is tricky. Quantum mechanics usually describes reality not as one definite path, but as a set of possibilities, weighted by probabilities. Some proposals for the early universe, like the Hartle-Hawking no-boundary idea, even suggest that time, near the beginning, behaves more like a spatial direction. In that picture, the universe doesn't start from a singular bang, but emerges smoothly from a kind of rounded geometry, where the notion of before simply doesn't apply in the usual way. Other ideas imagine the universe tunneling into existence from a quantum vacuum from nothing, in a very technical sense, where nothing is still a seething quantum state with laws and potential. In such scenarios, what came before might not be a previous time in the everyday sense, but a more abstract quantum condition. Asking what happened before time began becomes a little like asking what's south of the South Pole again. The concept doesn't map neatly. In an inflationary universe, quantum fluctuations don't just seed structure, they also blur the edges of the beginning. Some versions of inflation suggest it might be eternal to the future, spawning bubble universes like seeds drifting off a dandelion. Others hint it might be eternal to the past in some way, meaning our cosmic patch might be one blossoming in a larger, timeless garden of possibilities. In all of these, the simple picture of a single, sharp bang at t equals 0 softens into a more quantum, probabilistic story. You don't need to choose between these models tonight. Instead, feel their shared message. At the deepest levels we can currently probe, the beginning of time is not a clean, clock-like tick. It's a region where quantum uncertainty reigns, where small fluctuations matter enormously, and where the word before might have to be redefined or even let go. As you listen to your own breath, you can think of quantum fluctuations as the universe's original size, tiny, random exhalations that inflation carried across the cosmos. From those sighs came every star you've ever seen, every atom in your body, every thought you've had. The randomness wasn't noise. It was the raw material of form and story. Maybe, when you worry about chaos in your life, you can remember this. The cosmos itself uses little bits of uncertainty, tiny quantum flickers, to draw galaxies in the sky, and to make a place where, billions of years later, you can lie back and wonder how time began. Your existence isn't separate from those early fluctuations. It's one of their quiet consequences. In the next part of our journey, we'll step away from the question of before and turn toward a different mystery. Why, when the fundamental laws often work both forward and backward, your experience of time has such a clear direction from past to future, from remembered to unknown. For now, let the idea settle that the universe's earliest moments were not perfectly smooth or perfectly determined, but gently dappled by quantum chance, and that everything you see is the flowering of those first, microscopic tremors. You're still floating among those early quantum ripples, watching inflation stretch tiny jitters into the seeds of galaxies, when another question slides into your thoughts like a tide coming in. If so many of the universe's laws work perfectly well backward in time, why do you only ever remember the past and never the future? You blink slowly in the dark, feeling your own internal arrow of time. Your memories stack up behind you. Yesterday's conversations, last year's worries, moments from childhood like faded postcards. Ahead of you is blank, an unwritten space you call tomorrow. Every heartbeat pushes you in one direction only. You never feel time run in reverse. even though the deep equations of motion for particles almost don't care which way the movie plays. Physicists give a simple, powerful answer: entropy. Entropy is a way of counting how many microscopic arrangements correspond to the same macroscopic state. Picture a neatly stacked bookshelf. Every book in order, colors lined up, spines perfectly straight. There are only a few ways to arrange the books to get that exact look. Now imagine the same books tossed randomly into a pile on the floor. There are an enormous number of ways to make that messy heap. In this language, the tidy shelf is low entropy. The chaotic pile is high entropy. Now translate that into sensation. You can almost feel the difference in your body. A clean, orderly room makes your shoulders relax. A chaotic, cluttered room makes your mind buzz a little. Entropy is not exactly disorder in the emotional sense, but you can use that feeling as a guide. Low entropy is like neatly arranged energy and matter. High entropy is more spread out, more mixed, more ways to reshuffle things without changing what they look like from afar. The second law of thermodynamics says that for an isolated system, one that doesn't exchange energy or matter with its surroundings, entropy tends to increase. Over time, energy spreads out. Hot things cool down, cold things warm up, until everything approaches a uniform temperature. A hot cup of tea on your bedside table slowly surrenders its warmth to the room, never the other way around. You never see a cold cup spontaneously siphon heat from cooler air and grow hotter. That direction from more concentrated to more spread out is the arrow of time. Maybe the universe just loves to repeat patterns, because this same rule seems to guide everything from melting ice cubes to dying stars. On the level of tiny particles, forces may be time-symmetric, but when you add up unimaginably many particles, the odds overwhelmingly favor entropy increasing. There are just so many more high-entropy states than low-entropy ones. It's like rolling dice. There are many ways to get a messy mix of numbers, and only one way to get all sixes. Now zoom out to the universe. Early on, not long after the Big Bang and those inflationary ripples, the cosmos was hot, dense, and remarkably smooth. Matter and radiation were spread almost evenly throughout space, with only tiny fluctuations. At first glance, that sounds like high entropy. Isn't spread out the same as disordered? But gravity changes the story. For gravity, a nearly uniform distribution of matter is actually a low entropy state. There are far more ways for matter to clump into stars, galaxies, and black holes than to remain perfectly smooth. Clumped structures are gravitationally messier, with many micro-arrangements that look similar from far away. So the early universe, though hot, was gravitationally simple, a neat cosmic bookshelf waiting to topple. As time passes, gravity amplifies tiny differences in density. Slightly denser regions pull in more matter, becoming galaxies and clusters. Black holes form, which, as far as we can tell, are among the highest entropy objects in the universe. The cosmic bookshelf collapses into glorious, tangled piles of structure. Entropy increases, and with it comes the familiar direction of time. From smooth to clumpy, from simple to complex, from low entropy to higher entropy. You can feel an echo of this in your own body. You start life as a single cell, simple in shape but intricately ordered inside. Over time, your body and brain grow into an immense network of connections, then eventually begin to wear down. The processes that keep you alive, metabolism, cell repair, thinking, remembering, all work by taking in low entropy resources like food and sunlight and dumping higher entropy waste like heat into the environment. You're a temporary island of order maintained by increasing entropy around you. Here is where the arrow of time meets your inner world. Your memories form when your brain records information about the world, physically changing tiny patterns of synapses, strengthening some connections, weakening others. That process relies on irreversible steps. Energy is used, heat is dissipated, entropy grows. Remembering the past is inseparable from entropy increasing. You don't remember the future because it hasn't left such traces yet. The physical mark of what happened is always left behind you, lying in bed. You might imagine entropy as a soft, warm breeze flowing through everything. It takes the sharp temperature difference between your body and the air and smooths it out. It blurs the crisp edges of a sandcastle into a shapeless mound as waves and wind work away at it. It turns bright starlight into faint, uniform background glow over cosmic timescales. That steady smoothing, that spreading out, is what gives time its direction, what makes yesterday different from tomorrow. But there's still a deeper mystery, especially if you've been following the story of the cosmos. The second law tells you entropy increases toward the future. It doesn't tell you why it was low in the past. To have an arrow, you need a direction. To have a direction, you need an asymmetry. Why did the universe start in such a low entropy state, especially gravitationally? This question ties the thermodynamic arrow of time to the cosmological one. The universe's expansion from a smooth, hot beginning gives us both a direction in which the scale of the universe increases and a direction in which entropy rises as structures form and energy spreads. Some physicists argue that the low entropy beginning is simply a boundary condition. That's how the universe started, and we take it as given. Others search for deeper explanations. Perhaps in a larger multiverse, some regions begin with low entropy by chance, or perhaps our concept of entropy and time needs to be expanded in a quantum gravitational setting. For tonight, you don't need to solve that riddle. It's enough to see how the everyday arrow of time in your life, the way ice melts, your tea cools, your memories accumulate, is woven into the cosmic arrow, the one that runs from the Big Bang's smoothness to the present universe's rich complexity. You are, in a very real sense, a tiny agent of the arrow of time. Every thought you think, every dream you dream as you drift towards sleep, leaves a physical trace, nudging entropy upward in small, measurable ways. Your brain, your room, the faint warmth your body gives off into the night air, all are part of the same grand process that turns low entropy beginnings into high entropy futures. As your breathing slows, you might find comfort in this. There's a reason the past feels fixed and the future open. There's a reason broken cups don't reseal and spilled milk doesn't leap back into the carton. The universe's initial conditions and its statistical laws combine to give you a direction, an unfolding, a story. Maybe the universe just loves to repeat patterns, and one of its favorite patterns is this gentle, irreversible drift from ordered simplicity to spacious complexity. You lie there at one tiny point on that drift, your own life, a local arrow inside the cosmic one, carried along by entropy's quiet, relentless increase. The fact that you can notice it at all, can wonder why time feels the way it does, is itself one of the most beautiful consequences of a universe that began in a special, low-entropy state and has been unwinding ever since. You've followed the universe back through its expansion, its early quantum jitters, and the rise of entropy's arrow. Now, instead of rewinding further, you pause at a very special moment. Not the first instant, but the first time the cosmos becomes transparent enough for light to really travel. You're going to listen to fossil light. Imagine that the universe is young, about 380,000 years old. For a human, that's unimaginably ancient. For a cosmos, now 13.8 billion years into its story, its babyhood. Back then, everything is still hot, but not as violently hot as in the first seconds. The universe is filled with a dense fog of particles, protons, electrons, and photons. The photons, the particles of light, are constantly scattered, bouncing off electrons the way sunlight scatters in a thick cloud. No beam can travel far without being grabbed and redirected. It's like trying to see across a sauna filled with steam and swirling droplets. Your view is milky and undefined. In this early fog, light can't carry images very far. If you tried to look around, you'd see only a blazing, uniform glow. The photons are trapped in a cosmic game of pinball, ricocheting in all directions. The air in your room is nothing like this. It's thin and clear by comparison. Here, photons from your lamp or your phone can cross without being stopped very often. In that primordial plasma, they have no such freedom. But as the universe expands, it also cools. Temperature is a measure of average energy. Expansion takes that energy and spreads it out. Gradually, the photons lose some of their punch. The collisions grow less violent. At a critical threshold around 3000 degrees Kelvin, about as hot as the surface of a red star, the protons and electrons finally calm enough to combine into neutral atoms of hydrogen and helium. This moment is called recombination. When those charged particles lock together into neutral atoms, the fog suddenly thins. Electrons are no longer free to scatter light constantly. Photons, for the first time in cosmic history, can travel long distances without incessant interruptions. The universe becomes transparent. You can imagine it like a transition from thick, blinding fog to a clear sunrise. One moment, you can barely see your own hand. The next, the mist pulls back, revealing a wide landscape lit by a soft, even glow. In reality, what clears is the entire universe at once. Everywhere, almost simultaneously on cosmic scales, atoms form and light streams free. That released light is still around. It has been traveling ever since, crossing the expanding cosmos, wrapping around galaxy clusters, gliding through voids, passing silently through your body right now. It fills all of space. You are bathed in it as you lie there in the dark. Your eyes can't see it, because its wavelength has been stretched by billions of years of cosmic expansion, from visible light down into microwaves. But sensitive instruments can detect it easily. We call it the cosmic microwave background, CMB for short. You might picture it as a faint, warm whisper, a soft static that fills the universe. In fact, when old analog televisions displayed snow between channels, a tiny fraction of that random hiss was this ancient cosmic light washing over the antenna. Even now, if you could tune your senses to microwave frequencies, you would feel a uniform glow coming from every direction in the sky, like the low, gentle warmth from an oven that's been turned off but not yet cooled. This is fossil light, radiation that last physically interacted with matter nearly 13.8 billion years ago, when the universe was less than 1 million years old. Since then, it has mostly travelled freely, carrying with it a frozen image of conditions at the surface of last, scattering the photosphere of the universe, the last foggy layer before transparency. But the background isn't perfectly smooth. Remember those quantum fluctuations that inflation stretched out? They left some regions ever so slightly denser, and others a bit less dense. When the universe became transparent, these density differences showed up as tiny variations in temperature and density in the plasma, like subtle ripples on the surface of a pond. The CMB preserves those ripples. If you look at detailed maps of the cosmic microwave background like those made by satellites such as COBE, WMAP, and Planck, you see a speckled pattern of warm and cool spots. The differences are tiny, 1 part in 100,000. Yet from these faint, mottled patterns, cosmologists can read a story. The sizes and distribution of the spots tell us about the universe's geometry, its content, dark matter, ordinary matter, dark energy, its age, and how fast it's expanding. As you lie there, imagine the ceiling above you covered with a faint, mottled glow, patches only slightly warmer or cooler than their neighbours, in colours of red and blue just barely distinguishable. You run your hand through the air and feel almost nothing. The differences are too small for your skin. Yet for minds equipped with radio dishes and precise detectors, those tiny variations form a cosmic fingerprint. They are the earliest picture we have of the universe, a baby photo taken when it was just out of its foggy infancy. Maybe the universe just loves to repeat patterns, because this fossil light is like the echo in a cave after you shout, or the embers of a campfire long after the flames die down. The shout fades, the flames vanish, but traces remain. A faint sound, a lingering warmth. The Big Bang's fireball has cooled and faded, but its afterglow is still here, wrapping you in a 2.7 Kelvin bath of microwave light. It's as if the cosmos kept a quiet memory of its childhood and spread it out over the sky, waiting for someone to look closely. This light also carries a clue about the beginning of time as you experience it. The fact that the CMB is so nearly uniform, with only tiny variations, tells us that the early universe was remarkably smooth, and that different regions were somehow in close thermal contact, able to come to almost the same temperature, even those now widely separated across the sky. That's one of the puzzles inflation helps solve. By expanding a once small, equilibrated region to cosmic size, it explains why the CMB looks so even. In other words, this fossil light doesn't just show you what the early universe looked like, it hints at how it got that way. As your thoughts slow, you might take comfort in knowing that we are not guessing blind about the early universe. We are listening to this fossil light with exquisite care. Its spectrum, the way its intensity varies with frequency, matches almost perfectly the theoretical shape of a blackbody at 2.7 Kelvin, just what you'd expect from a cooling thermal glow. Its tiny anisotropies, those speckles in temperature, align beautifully with models that include dark matter, dark energy, and an inflationary beginning. You live in a universe where the past has left its fingerprints, not just in rocks and fossils on Earth, but in the very fabric of the sky. Every time you see a picture of the cosmic microwave background, those blue and red mottled oval maps, you are looking at a translated version of that fossil light, turned into colors your eyes can understand. Tonight, you don't need a telescope. You can simply imagine that ancient glow flowing quietly through your room, through your body, through every wall and rooftop. The universe is not dark. It's gently lit by the faded memory of its own birth. Time, which felt like an abstract coordinate in earlier sections, now feels like a concrete distance. The span between that first free light, 380,000 years after the beginning, and the moment you are lying here, listening, perhaps you breathe a little deeper, knowing this. The fact that we can reconstruct so much of the universe's history comes from light that has traveled almost the entire age of the cosmos, never quite lost, only stretched, cooled, and softened. The same laws that let that light travel, unbroken, also guide the photons from your lamp, the warmth from your blanket, the signals in your brain. The beginning of time, as far as we can see it, is recorded not in words or symbols, but in this pervasive glow. The cosmic microwave background is a message from the young universe, written in temperature and pattern instead of ink. You are part of the first species, as far as we know, to read it consciously and to ask, what does this fossil light say about where time itself began? Let that thought gently settle over you, that even as you drift towards sleep, you are wrapped in ancient light, bearing news from a time when there were no stars, no planets, no eyes to see only a hot, expanding cosmos, already preparing the stage for everything that would one day come, including you. You're drifting now in a universe that has cooled enough for fossil light to travel, that has grown an arrow of time from low entropy beginnings, but your mind keeps circling back to that trembling edge near the Planck era, where our equations blur. You sense that general relativity and quantum mechanics, the two great pillars of modern physics, are both whispering at once, and their voices don't quite match. What if, at the deepest level, time itself is not what it seems? Imagine you're standing at the boundary between two forests. Behind you is the smooth, dark pinewood of space-time, Einstein's realm, where time is a continuous dimension, bending with gravity. Ahead of you is a strange, crystalline forest of quantum rules, where reality comes in quanta, probabilities, and superpositions. Somewhere in the tangled roots between these forests, new kinds of trees grow, loops and strings. First, you wander into the land of loops. Loop, quantum gravity. In this picture, space-time is not a smooth sheet at all, but woven from tiny, discrete loops, like an invisible chainmail that's far too fine for your senses to notice. At large scales, those loops blur into smoothness, the way individual threads blur into a single, soft bedsheet. But if you could shrink yourself down, far smaller than any particle you've ever heard of, you'd see a different texture. Close your eyes and imagine space as a dark, three-dimensional lacework. Little links and nodes connect in a vast network, shimmering softly. Each node carries a quantum of volume. Each link carries a quantum of area. There is no between the loops, no continuous in-between space. The loops are the space. When you move your hand in front of your face, in this deep description, you're not sliding through a smooth void. You're stepping from node to node in an unimaginably fine quantum lattice. In such a world, the Big Bang singularity may dissolve. Instead of space-time curvature shooting off to infinity as you rewind, the quantum granularity of geometry resists being squeezed beyond a certain point. Some loop quantum cosmology models suggest a bounce. A previous contracting universe shrinks until quantum geometry becomes dominant, then rebounds into expansion. Time, instead of starting from an absolute beginning, might extend through a before, tied together by quantum gravitational rules. But here is the twist. In many of these formulations, the fundamental equations look timeless. There's a famous equation, the Wheeler-DeWitt equation, which, in its simplest form, doesn't contain time at all. It just says that the total wave function of the universe is static, unchanging, no ticking, no flowing. It's as if the universe's deepest description is like a still photograph rather than a movie. So where does your sense of time come from if the master equation is frozen? One idea is that time is relational. You don't need an external clock. You need changing relationships between parts of the universe. Picture all those loops of quantum geometry and all the fields that live on them as part of a single, vast state. Even if the state as a whole doesn't evolve in some external time, different parts of it can serve as clocks for other parts. One pattern changes relative to another, and from that network of changes, something like time emerges. You can feel an echo of this when you lie in the dark. If you strip away the clock on your phone, the schedule of your day, even the rotation of Earth, you still have rhythms. Heartbeat, breath, the slow cycles of sleep. One process in your body can measure another. Time, for you, is not an external entity, it's a web of changes, each one compared against the others. Maybe the universe just loves to repeat patterns. On the largest scale, its own internal degrees of freedom keep track of one another, giving rise to time as experienced by beings within it. Now you cross into the land of strings. Here, the fundamental objects are not point particles but extraordinarily tiny strings, vibrating in many possible modes. Each note of vibration corresponds to a different particle: graviton, photon, quark. The strings may live in a space-time with extra dimensions, curled up so tightly you never notice them, like tiny rolled carpets hidden beneath your bedroom floor. In some string-theoretic cosmologies, what you call the Big Bang could be the result of brains' higher-dimensional sheets colliding or interacting. In others, the early universe is described by a pre-Big Bang state, or by dualities, where what looks like a beginning in one description is a transformation in another. Time, again, becomes slippery. What seems like a starting point in our four-dimensional picture might be just a corner of a larger, more symmetric story. String theory also gives you a different angle on emergent spacetime. In certain setups like the ADS, CFT correspondence, gravity in a higher dimensional spacetime is mathematically equivalent to a quantum field theory without gravity on a lower dimensional boundary. The geometry inside can be encoded in quantum entanglement patterns outside. It's as if the shape of a room could be completely reconstructed from the relationships among the paintings on its walls. If spacetime geometry can emerge from entanglement, then time, too, might be an emergent bookkeeping of correlations. Imagine your mind as a tapestry of neurons, each with its own activity, and your sense of a flowing now as something that arises from their changing patterns, not from an external clock. Zoom out, and the universe's time might be a similar tapestry, woven from the entanglement of its deepest degrees of freedom. All of this can sound dizzying, so bring it back to something you can feel. Lying here, your body is at human scale, your thoughts at human speed. To you, time is a gentle river, seconds, minutes, hours, years. But the loops, strings, and timeless equations are like the microscopic molecules of that river. At their level, the water might not flow in any simple way. Instead, there are vibrations, interactions, static equations relating one configuration to another. Only when you step back and average over all that detail does a smooth current appear, does time feel like something that moves. In this view, asking how did time begin becomes a bit like asking at exactly which droplet did the river start. The river might be a large-scale pattern arising from something deeper and more still. The Planck era, the bounce, the brain collision, or the quantum state before the Big Bang could all be ways that underlying timeless rules give rise to a regime where something like cosmic time turns on and starts to behave smoothly. You don't have to choose between loops and strings tonight. Both are works in progress, mathematical lanterns probing the dark. They may both capture pieces of the truth, or both need to be replaced by something we haven't yet imagined. What matters for your bedtime journey is the shared suggestion. That time, the quiet current you feel in your chest, might not be fundamental. It might be the music, not the instrument, the melody arising when fundamental notes are played together. As your lids grow heavy, you can hold a simple image. Far below your awareness, the universe is described by deep, perhaps timeless rules loops of quantum geometry, vibrating strings, intricate webs of entanglement. From these, a smooth space-time emerges, with an arrow of time, with expanding galaxies and cooling stars, with beings who count days and tell stories before sleep, and you are one of them. resting tonight on a small world, inside a vast, emergent cosmos, rocked gently by a river of time that may itself be a shadow of something even more quiet and profound. You're lying there, feeling time as a gentle river carrying you forward, when another possibility slips in like a dream. What if this river doesn't start from a single spring and end in a distant ocean, but loops, cycles, or branches in ways your everyday intuition never sees? So far, we've followed a story where the universe has a kind of beginning, a hot, dense state, a Planck-scale mystery, then expansion, cooling, and structure. But some cosmologists quietly ask a different question. What if the Big Bang is not the first page, but just a chapter break? Imagine yourself hovering again near that extreme early moment where our usual space-time picture wobbles. Now, instead of seeing a hard wall time stopping at a singularity, you picture the universe as a vast, elastic ball being squeezed. As it contracts, everything comes closer together. Temperatures rise, structures break down. But instead of collapsing into a mathematical abyss, the ball reaches a point where further compression becomes impossible. Quantum gravitational effects, like those loops and strings from the last section, push back. Then, like a heartbeat, the universe bounces. In a bounce cosmology, you have a previous contracting phase before our current expansion. Time stretches back before the Big Bang, not into nothingness, but into a different cosmic era. If you could stand in that previous universe on some ancient planet, looking at some ancient sky, you'd see galaxies moving closer together, not farther apart. Your arrow of time would still point from lower entropy to higher entropy. Your memories would still be of the past. But viewed from our side, your whole era leads into the squeeze that becomes our bounce. You can give this a sensory feel. Picture yourself in a grand hall with a high, domed ceiling. At first, the walls are slowly drifting inward, the air warming, the sound of distant echoes growing louder as space tightens. Then, at a critical moment, the walls stop and surge outward, the air rushing past you in a cool blast. The floor vibrates, and suddenly there is more room, more space, and the hall begins a new phase of expansion. The contracting phase was one half of a breath. The expansion you live in is the exhale. Some models of loop quantum cosmology naturally lead to such bounces, where the quantized nature of space-time geometry prevents the formation of a true singularity. Instead of time beginning, it continues through a highly compressed bridge connecting two phases. Maybe the universe just loves to repeat patterns, a heartbeat, a breath, a bouncing cosmos. Other ideas talk about cycles on even grander scales. You might have heard of cyclic or ekpyrotic models, where the universe goes through repeated phases of slow contraction and violent renewal. In some versions, our universe is like a three-dimensional brain floating in a higher dimensional space. Every so often, it collides with another brain. Each collision is experienced by inhabitants of the brain as a kind of Big Bang, a sudden injection of energy, heating, and expansion. After a long period of cooling and structure formation, the brains drift apart, then are drawn together again by higher dimensional forces, preparing for the next collision, the next bang. Imagine two immense, invisible sheets gliding toward each other in the dark. Between them, there is a quiet, eerie tension. When they finally touch, there is no noise sound needs air, but in the higher dimensional arena, fields flare, energy floods in, and a new hot beginning is born. From your perspective, inside that event, you feel only the heat, see only the glow of a new, expanding cosmos. You have no direct memory of the previous cycle, just as you don't remember your earliest moments as an infant. But the pattern continues, cycle after cycle, like the swing of a pendulum on incomprehensible timescales. Another cyclic possibility is more subtle, conformal cyclic cosmology. Here, the idea is that the very distant future of the universe, when all matter has decayed, black holes have evaporated, and only thin, cold radiation remains, can be mathematically reshaped to look like a new Big Bang. In a certain conformal sense, where only the angle of trajectories matters and absolute scales are ignored, the end of one aeon can line up with the beginning of the next. Time, in this picture, is a series of vast cycles, each beginning hot and dense, ending cold and dilute, linked by a transformation that erases scale. In your mind's eye, picture a series of circles drawn one inside another, like ripples on a pond frozen in ice. Each circle is an aeon, a complete universe from Big Bang to final fade. The innermost circle touches the next as if handing over a baton, not through a tunnel or bounce, but through a change in how you measure size and time. To beings within any one circle, time feels like a one-way journey, from beginning to end. To a mathematician, looking at the whole pattern, those journeys repeat, nested and connected. Then there is the multiverse. Perhaps not cycles in time, but a branching of realities in space and possibility. In some versions of eternal inflation, the inflating space-time never completely stops. It keeps bubbling, like a pot of water that never fully boils away. Each bubble is a pocket universe, a region where inflation ends and a hot Big Bang-like phase begins. Our observable universe is one such bubble. Others may exist beyond our horizon, forever unreachable. From the vantage point of this vast inflating backdrop, beginnings are local. Time in one bubble starts when inflation ends there. Time in another starts at a different moment. The overall multiverse may have no single, universal beginning, just an endless, frothing sea of bubble births. You, lying in your room, exist deep inside one such bubble, far along its history, with your own Big Bang as your time zero. But the larger story might be messier, more sprawling, more like a cosmic tree with countless branches and no obvious first leaf. All these plots, bounces, cycles, multiverses are speculative. They are attempts to extend our story of time beyond the Big Bang we can currently probe. Some leave imprints we might one day detect, subtle patterns in the cosmic microwave background or in the distribution of galaxies. Others remain more philosophical, constrained by consistency and mathematical elegance rather than clear observational signatures. As you listen, there's a temptation to ask which one is true. Does the universe bounce? Does it cycle? Is there a multiverse? Or is our simple Big Bang model, with a single low-entropy beginning, all there is? Tonight, you don't have to decide. What matters for your journey is the shape of the question. These models all share one deep idea, that what you call the beginning of time might not be an absolute boundary. It may be a transition, a phase change, a local dawn in a bigger, stranger landscape. You can feel a reflection of this in your own life. There are events that feel like beginnings, your first day at school, a move to a new city, the start of a relationship. But if you zoom out, each of these beginnings is connected to earlier stories, choices your parents made, histories of places and cultures, long chains of events you never saw. Maybe the universe just loves to repeat patterns, and its Big Bang is one such beginning, real and meaningful within your patch, yet connected to deeper threads you can only glimpse through theory. As your eyes grow heavier, imagine the cosmos as a vast, breathing organism. It may inhale and exhale through bounces, live through successive aeons, or sprout endless branches of inflating space. Within one tiny lungful of that breath, you live your entire life, from first cry to final sigh. Your arrow of time feels straight and finite, yet it may be one strand in a tapestry of cycles and branches that stretches far beyond what you can see. For now, you can rest with a simple, calming thought. Whether time began once or many times, whether our universe is a lone story or one chapter in an endless saga, the moment you are in is real and complete. The river of time you float on is enough for a human lifetime of wonder, even if, far beyond, the cosmos is busy writing sequels, prequels, and parallel tales. You're lying very still now, wrapped in the idea of cosmic time, expanding universes, arrows of entropy, quantum beginnings, when another, quieter question rises. If no one were here to notice it, would time still exist? You feel your own sense of time immediately, the slow rhythm of your breath, the way this sentence unfolds word by word. Time, for you, is inseparable from experience. It's the thickness of the present, the way a memory glows behind you and an expectation hovers ahead. But physics often talks about time as if it's out there, like a landscape that exists whether or not anyone walks across it. Imagine, for a moment, that every conscious being in the universe gently falls asleep at once. No eyes to see, no ears to hear, no thoughts to mark now. Planets keep orbiting their stars. Stars keep fusing hydrogen into helium. Galaxies drift and collide without witnesses. Radioactive atoms still decay. Black holes still tug on nearby matter, photons still stream through the void. In the language of physics, the equations don't care that there's no one awake. Processes still have durations. Events still have order. The world lines we spoke of earlier still thread through spacetime. From this perspective, time is a feature of the universe, independent of observers. It's part of the geometry, a dimension in which things can happen. The parameter that appears in the laws, whether or not any brain is around to whisper later. If you could float above all consciousness, you'd still see supernovas blossom and fade like brief, silent fireworks in the dark. You'd still be able to say, this happened before that, by how far apart they sit on the cosmic timeline. Now, zoom back into your own skull. Here, the story gets stranger. Neuroscience tells us that your brain doesn't simply receive time, it constructs it. Signals from your eyes, ears, skin, and inner organs all travel at different speeds, taking different routes. Yet, your experience of now feels unified. The sound of my voice in your mind, the weight of your blanket, the faint hum of outside traffic all seem to arrive together. To weave this unity, your brain holds onto incoming data for a brief window, fractions of a second, and stitches it into a coherent moment. You can give this a sensory test. Think of watching lightning flash and hearing thunder. The light arrives almost instantly. The sound lags behind. But your brain can flex its sense of now to bind them into a single event, a storm out there happening in real time. In experiments, when people see a stimulus slightly before or after a related sound, the mind often adjusts, sliding the moments together or apart to keep the story smooth. Time, in your head, is more like an edited film than a raw, uncut feed. There are illusions that make this vivid. When an unexpected, oddball image appears, say, a strange shape amid a stream of identical pictures, people often report that it seems to last longer, even when it's on the screen, for the same duration. Adrenaline can stretch seconds into what feels like minutes during a car accident. Psychedelics can make time fragment or loop. Boredom can inflate minutes. Joy can compress hours. In your brain, time is elastic, colored by emotion and attention. Maybe the universe just loves to repeat patterns, because the way your mind assembles time echoes the way physics might assemble time from deeper structures. Just as quantum gravity may turn a timeless equation into an emergent flow when seen from within, your brain takes timeless electrochemical events and turns them into a felt river. In both cases, the flow may be a perspective, not a fundamental ingredient. Philosophers of physics sometimes talk about the block universe. In this view, past, present, and future all coexist in a four-dimensional space-time block. Your birth, this moment in bed, and your distant future are all laid out like different locations in a vast landscape. The flow of time, the sense that you are moving from one moment to the next, is an internal feature of consciousness moving along its world line, not an objective property of the block itself. The universe, in that picture, doesn't change. Different times simply are. Change is the difference between slices. Contrast that with how it feels from the inside. For you, only the present is vividly real. The past is accessible only through memory and records. The future through prediction and imagination. When you recall a childhood afternoon, you can feel the sun on your skin, smell the grass, hear a distant laugh, but you also know it's not happening now. Your brain is reconstructing a pattern from stored traces. When you imagine tomorrow, there are no sensory records yet. Your mind plays with possibilities, guided by experience and desire. Some philosophers argue that this presentness is a fundamental feature of reality, that only the present is truly real, and the past and future are in some sense lesser. Others, closer to the block universe view, see the present as a spotlight sweeping across an already existing stage. Modern physics itself tends to lean toward the block. Its equations don't single out a special now, but our inner experience clings stubbornly to the feeling of a moving spotlight. What do we make of this mismatch? One way to reconcile them is to think of two layers. On the outer layer, there is the physical time in the equations, a parameter that orders events and appears in dynamical laws, whether or not anyone is watching. On the inner layer, there is psychological time, your constructed flow, shaped by neural machinery, emotion, metabolism, and memory. Psychological time rides on physical time but doesn't mirror it exactly. It compresses, stretches, and sometimes breaks. You can feel this difference easily. Lie there and count. 1, 2, 3, matching each number to a breath. Then think of a moment when you were utterly engrossed, lost in music or conversation or a game. Time, in those moments, often seems to vanish. Yet physically, seconds ticked by at their usual rate. Your inner clock and the universe's outer clock are related but not identical. So, does time exist without observers? On one level, yes. Radioactive isotopes decay, stars age, galaxies collide, and those processes have durations that can be measured by any device, conscious or not. The universe's history, its expansion, its cooling, its transitions from plasma to atoms to stars unfolds according to laws that make no explicit reference to minds. On another level, the feeling of time, the sharp border between now and not now, the way your life arranges itself into a narrative with a beginning, middle, and anticipated end that is inseparable from observation, memory, and consciousness. Without observers, there may still be time, but there is no one to call it earlier or later, no story, no sorrow over the past or hope for the future. As you drift closer to sleep, you can hold both views at once. Outside, the universe carries on, indifferent and majestic, its cosmic clock ticking through nuclear reactions and orbital motions. Inside, your brain gently winds down its own clock, stretching and softening seconds into something slower, dreamlike. Physical time will continue whether or not you notice it. Psychological time will ebb as your consciousness dims. And perhaps that's a comforting thought, that the river of cosmic time doesn't depend on your vigilance. It was flowing long before you arrived, and it will flow long after, while your own inner sense of time rises, sparkles for a while with memories and meanings, and then eases back into quiet. The universe's story and your story share the same timeline, but they are written in different inks. You've drifted so far outward into quantum foam, inflating space, fossil light, that it's easy to forget something simple and intimate. You are yourself a tiny, living clock, ticking quietly inside the vast machinery of cosmic time. For a moment, leave galaxies and big bangs behind and come home to your body. Feel where it touches the bed, the slight pressure at your shoulders and hips, the way fabric folds under your fingers. Beneath the stillness, thousands of rhythms are at work, layering over one another like soft percussion in a slow song. Start with the one you know best, your heartbeat. If you pay attention, you can feel it. Faint but insistent thump, rest, thump, rest. Each beat is a pulse of blood pushed through arteries and veins, carrying oxygen and nutrients, gathering carbon dioxide and waste. Your heart is a biological metronome, driven by a cluster of specialized cells in the right atrium called the sinoatrial node. These cells spontaneously generate electrical impulses, setting the pace. Left alone, they would keep firing. They don't need your permission. Electrical waves travel through the heart's conduction system, causing muscles to contract in a precise sequence. First the atria, then the ventricles. Every beat is a coordinated dance of ions, sodium, potassium, calcium, flowing through channels in cell membranes. At the microscopic level, it's a story of charges and diffusion, governed by the same physics that shapes stars and plasmas. At your scale, it's the steady drum behind your life. You can imagine each heartbeat as a tiny tick of your personal time. Doctors can quite literally read your cardiac rhythm as a time series, peaks and valleys on an electrocardiogram. When the pattern falters too fast, too slow, irregular, you feel it in your chest, in your energy, in your sense of how the day flows. Maybe the universe just loves to repeat patterns. The same laws that describe oscillations in early universe plasma also describe the oscillations in your heart. Now notice your breathing. Inhale and exhale. Your lungs follow their own rhythm, slower than your heartbeat, tuned by neural circuits in the brainstem that monitor levels of carbon dioxide and oxygen. When you fall asleep, that rhythm changes deeper, more regular in some stages, lighter and more irregular in REM sleep. If something startles you, your breath quickens. If you calm, it lengthens. Each cycle is a wave of air, exchanging gases with the blood your heart pumps. For a few breaths, imagine you're listening to yourself, as if from outside. You're like a small planet with two main cycles, A fast beat, heart. A slower swell, lungs. If you could draw your own world line through space-time and mark each heartbeat as a dot, you'd see a nearly regular spacing. Even as your mind wanders, your internal clocks keep a steady count, silently advancing you through your allotted slice of cosmic time. Beneath these rhythms lies a deeper one, your circadian clock, the roughly 24-hour cycle that shapes your sleep, your temperature, your hormone levels, your mood. At the center of this system is a tiny region in your brain called the suprachiasmatic nucleus, the SCN, nestled just above where the optic nerves cross. It's a knot of neurons that act like a master clock, coordinating timing signals throughout your body. These neurons keep time through molecular feedback loops. Certain clock genes are activated, producing proteins that accumulate and then, after a delay, shut down their own production. As the proteins degrade, the cycle begins again. It takes about 24 hours. Each cell's rhythm is like a tiny drummer with its own beat, and the SCN synchronizes them into a band. Light hitting your eyes, especially blue light in the morning, resets the phase of this master clock, aligning your internal day with the astronomical day of Earth's rotation. You can feel this circadian rhythm in subtle ways. Your body temperature dips in the early morning, rises through the day, then falls again at night. Hormones like cortisol peak in the morning to wake you. Melatonin rises in the evening to make you drowsy. When you cross time zones, quickly flying from one part of the world to another, your inner clocks lag behind the local day-night cycle, and you feel jet-lagged, sleepy at noon, awake at midnight. It's like your body is out of sync with the cosmic drum of Earth's spin. Think about that for a second. Your internal day is literally entrained to the turning of a planet in space. The same rotation that gives you sunrise and sunset also trains gene expression in your cells. The beginning of your subjective day, when you naturally wake, when you feel alert, is a reflection of orbital mechanics and axial tilt, filtered through biology. The origin of time in your experience is tethered to the motion of a rock around a star. Zoom in further, and you find even finer clocks. Neurons in your brain fire in patterns of spikes, some at slow, dreamy rhythms, others in fast, precise bursts. Networks of neurons can oscillate in different bands: theta waves, alpha waves, gamma waves. These rhythms help coordinate perception, memory, and action. For example, certain oscillations appear when you form new memories, binding together sights, sounds, and emotions into a coherent episode. Time in your mind is partially encoded in how these patterns unfold. Experiments show that your sense of time intervals, like judging whether a sound lasted half a second or a whole second, involves distributed neural circuits. Some theories propose that your brain keeps time by tracking the evolving state of these networks. Time is represented not by a single ticking mechanism, but by the trajectory of activity through a high-dimensional space. Your now is a pattern, and its change is your subjective time. Lying in bed, you can picture your brain as a dark city at night, lights flickering in patterns. Some neighborhoods pulse slowly, others shimmer rapidly. Together, they create a moving tapestry. As your consciousness drifts towards sleep, certain rhythms grow dominant, others quiet. The city doesn't shut down, it shifts into a different mode. Your internal clocks keep ticking, even as your awareness of time blurs. Maybe the universe just loves to repeat patterns, because there's another echo here. Just as cosmologists use standard candles and standard clocks to measure cosmic time, your body uses standard processes: heartbeat, breath, gene cycles, neural oscillations to organize your inner time. If your heart suddenly doubled in speed, the same number of beats would correspond to half as many seconds. If your circadian rhythm shifted by hours, your sense of day and night would slide against the stars. Biological time is anchored to physical time, but it has its own calibration. All these internal rhythms exist inside the larger arrows we talked about earlier. Your body is constantly fighting entropy, maintaining order by taking in energy and dumping heat. That battle has its own timeline: growth, maturity, aging. Cells accumulate damage, repair mechanisms eventually falter. Mitochondria, telomeres, stem cells all have clocks of their own. The beginning of time for you personally is not the Big Bang, but the moment your cells first began to divide in a particular pattern. Embryonic development, the start of your life's arrow. Yet even that beginning is layered atop older timescales. The evolutionary history of your species, the origin of life on Earth, the formation of our planet, the birth of our star, the synthesis of heavy elements in ancient stars, the Big Bang itself. Your little clocks are built from atoms forged in stellar cores, arranged by DNA sequences refined over billions of years. Your heartbeat is, in a sense, the echo of nuclear furnaces and supernovas slowed down into human tempo. As you lie here, you can think of yourself as a bridge between timescales. On the fastest end, quantum events flicker in your molecules. Slightly slower, neural spikes fire, muscle fibers contract, chemical reactions proceed. Slower still, circadian rhythms, menstrual cycles, seasonal shifts, aging, and beyond you, planetary orbits, stellar lifespans, galactic rotations, the expansion of the universe. Each layer has its own beginning of time question, its own way of dividing before and after. For tonight, you don't need to juggle them all. Just listen, gently, to your own. Feel your pulse, however faint. Notice the rhythm of your breathing. Sense the tug of your circadian clock inviting you towards sleep. These are your local markers of time's flow, tiny internal big bangs and arrows unfolding quietly within the grand cosmic timeline. The same universe that began in a searing, formless blaze now contains you, a being who measures seconds with heartbeats, days with sunrises, years with birthdays, and an entire life with memories that stack like stars in your inner sky. Times beginning in the cosmos and times beginning in your body are not separate stories. They're pages of the same book, written at different scales. And right now, one of your clocks, the one that knows when it's time to rest, is gently, insistently telling you, slow down, let go. Let all these rhythms sink into the background hum as you drift deeper into the soft, dark current of sleep. You're lying here, wrapped in blankets and background starlight, with a strange double awareness. On one side is the scientific story you've been travelling through. A universe with a hot beginning, an arrow of time, quantum jitters, expanding space. On the other side is something quieter and more personal. Your life, threaded through that story like a single, delicate line of silk in a vast tapestry. If time really had a beginning in the cosmos, if there was a first meaningful moment for space-time as we know it, what does that mean for you, a tiny, conscious flicker so far downstream? For a moment, imagine the entire history of the universe compressed into a single day. Midnight, the Big Bang. In the first fractions of a second, space inflates, particles form, forces separate. By 1 a.m., the cosmic plasma glows, thick and brilliant. By 3 a.m., atoms emerge. The universe goes transparent. Fossil light begins its long journey. Galaxies form in the morning, stars in the late morning and afternoon. Our sun doesn't light up until evening. Earths, oceans, and early life are a late-night phenomenon. Complex life, dinosaurs, forests, all in the last minutes. On this scale, your entire life, every memory you hold, every joy and heartbreak, fits into less than a blink just before the final midnight. You're a breath on the lips of a universe day that has been exhaling for billions of years. That can feel unsettling. You might sense a tug of smallness, as if your experiences are too fragile to matter against such immensity. You are finite twice over, in space, occupying a tiny patch of a small planet, and in time, inhabiting a short interval on a long, cosmic clock. But consider the opposite. If the universe were infinite in time, with no beginning and no end, it could be just as dizzying. An eternal universe might make every event feel lost in an endless sea, repeated infinitely often, stripped of uniqueness. A universe with a beginning and perhaps an end gives your life a different kind of context. You are part of a story with a shape. Maybe the universe just loves to repeat patterns, because stories are often like that. They begin, they develop, they conclude. A book with infinite pages and no structure is hard to read. A song that never ends, with no introduction or finale, is hard to feel. The universe is time finite so far as we can see backward. Perhaps finite forward too gives your existence a frame, a before you and an after you. Even if those are unimaginably vast, you can feel this in your body. Think of how different it feels to have a whole lazy Sunday ahead of you versus a single free hour at the end of a long day. The short, finite hour can feel more precious, more focused. you savor it. The finiteness doesn't diminish its value, it sharpens it. Your life is like that hour compared to cosmic history. You are not less meaningful because you are brief. You are meaningful in a way that depends on being brief. From the standpoint of physics, the universe doesn't assign purpose. It evolves according to laws, with no built-in notion of should or ought. Hydrogen clouds do not feel obligated to become stars. They simply follow gravity and thermodynamics. Entropy doesn't care whether you write a poem or scroll your phone. It increases either way. And yet, lying here, you feel meaning. You care about certain things more than others. People you love, projects you've poured yourself into, memories you treasure. That caring is not an illusion. It's a real pattern in your brain and body, encoded in synapses and hormones and behaviors. It's a local fact in the universe, just as solid as the orbit of the moon or the glow of a nebula. You might think of meaning as something that emerges when a time-bound, memory-bearing creature like you looks out at the world and in at itself. The laws of physics allow atoms to arrange into molecules, molecules into cells, cells into brains. Those brains can represent the world, remember the past, imagine the future. From that capacity comes value. The ability to prefer one outcome over another, to say this is good or this hurts, to weave moments into a narrative you call my life. In that sense, the beginning of time in the cosmos is like a distant prologue, the opening chord that set the stage for meaning to arise billions of years later. Without a universe that expands and cools, that forms stars and heavy elements, that allows planets and chemistry and biology, there would be no minds to ask why at all. The fact that time began, in a physical sense, is a precondition for your ability to feel that your finite time matters. Take a breath and notice how your chest rises and falls. Each inhale is a tiny defiance of entropy. Oxygen flows in, fuels ordered processes in your cells. Each exhale releases heat and carbon dioxide back into the world. Your body is a local reversal of the slide toward uniformity, paid for by increasing disorder elsewhere. You are literally a small, temporary oasis of structure in a universe whose overall entropy is rising. That oasis is where meaning lives. This doesn't mean the universe is designed for you in any simple way. It means that given enough time after the beginning, given the right conditions, pockets appear where complexity blooms. You are one of those blooms. From your vantage point, your finite span is everything. The beginning of cosmic time is abstract. The beginning of your time, your first memory, your earliest feelings of self is immediate. You might wonder about the end. Cosmology suggests several possibilities. Eternal expansion into a cold, thin heat death. A big crunch, a big rip, endless cycles or multiverse branches. Each paints a different picture of time's long-term horizon. In most of them, individual lives, planets, even galaxies are transient. On cosmic scales, everything familiar fades. But notice something gentle here. The possible end of time doesn't erase your experiences now. The joy you felt listening to a favorite song, the kindness you showed a friend, the awe you had the first time you saw the Milky Way. Those are real events, embedded in space-time, as real as any supernova. They occur, and then they're done, but their having happened is not undone by what the far future holds. Think of a painting in a gallery. The moment the artist finished it is long past. Their life may be over. Yet the painting exists, a record of colour and form. Your past moments are like that in the block universe picture. They are there along your world line, even if your consciousness has moved on. The finiteness of your timeline doesn't negate the reality of the segments already drawn. Maybe the universe just loves to repeat patterns, because we often find meaning in things precisely because they end. A summer that can't last. A conversation that eventually falls quiet. A life that is finite. Knowing that time is limited cosmically, biologically, can make you more attentive to this moment. The feel of the sheets, the rhythm of your breath, the strange luxury of being able to ponder the beginning of time at all. From stardust and thermodynamics, from quantum fluctuations and expanding space, a creature has emerged who can tell stories before sleep. That creature is you. You are not outside the universe, looking in. You are the universe looking at itself from the inside, for a little while, through human eyes. The question, how did time begin, unfolds into another. What will I do with the time I have? You don't need a grand cosmic mission to answer that. It can be as simple as being kind more often than not, curious more often than indifferent, present more often than distracted. In a universe that doesn't mandate meaning, these are ways you make meaning. Small, deliberate patterns in the flow of your finite time. As your thoughts grow softer, you can hold this. The beginning of time in the cosmos is a mystery we approach with equations and telescopes. The meaning of time in your life is a mystery you shape with choices and attention. Both are real, both are unfinished, and both, somehow, meet here, in this quiet room, in this passing moment, with you listening and breathing as the ancient universe keeps unfolding around you. You're still holding that double awareness from before, the vast, mathematical sweep of the universe, and the small, warm immediacy of your own life. Now we come to the simplest part of the story, where you don't have to travel to the beginning of time or the end of it, but rest right here, in the middle of an ongoing universe. As you lie there, nothing dramatic seems to be happening. The room is quiet, the air is still. Yet on the largest scales, this moment is anything but empty. Right now, as your chest rises and falls, stars are being born in dark clouds of gas, their cores igniting one by one like distant candles. Other stars are dying in supernovae, petals of plasma blooming and fading in the black. Whole galaxies are colliding in slow motion, their shapes warping over hundreds of millions of years. The cosmic expansion continues too. Space itself keeps stretching, carrying galaxies away from each other on average, like tiny boats drifting apart on a tide. Dark energy, the mysterious something that accelerates this expansion, quietly does its work. If you could zoom out until your room, your city, your planet, and even your galaxy shrank to a single dot, you'd see countless other dots, all receding within a fabric that refuses to sit still. From the viewpoint of physics, this is just another slice of cosmic time, characterized by particular values of things like the Hubble parameter, the average density of matter, the temperature of the cosmic microwave background. It's a specific now in the universe's history, defined by numbers and equations. From your viewpoint, it's the softness of your pillow and the sound of your own breathing. Maybe the universe just loves to repeat patterns, because the way it flows through this moment mirrors what it did at the beginning. Follow its laws, the same constants that shaped the Planck era and the Big Bang, C, G, H. The strengths of forces are at work here, in the chemistry of your cells and the glow of your devices. Nothing special has been turned on for your benefit, and yet, somehow, conditions are just right for you to exist, to think, to wonder about how time began. You've traced that story backward, through biological rhythms and memories, through the arrow of entropy, through fossil light and inflation and quantum foam, all the way to the threshold where our theories flicker. You've seen how, for physics, the beginning of time often means the edge of where our laws can speak clearly. Beyond that edge lies speculation, bounces, cycles, multiverses, emergent time. Now, drifting at your own speed, you can turn the perspective around. Instead of staring anxiously toward the unreachable start, you let your attention rest on the fact that time is still unfolding, and you are being carried along by it, effortlessly. The universe does not need you to keep it running. Nuclear reactions in distant stars don't pause if you close your eyes. Galaxies don't hold their breath when you fall asleep. Even your own body is mostly on autopilot. Heart, lungs, circadian rhythms, immune surveillance, all ticking along without your conscious supervision. The universe is still here, quietly working while you sleep. There's a kind of safety in that. The weight of keeping track of everything is not on you. Time began, however, precisely that happened long before you, and it will continue long after. Your task is gentler, to inhabit your small stretch of it as fully or as peacefully as you can. If you think back to the beginning of this journey, we started with a simple idea. Time as change. Breath in, breath out. One moment different from the next. That humble definition has grown to encompass cosmic expansion, gravitational curvature, quantum uncertainty, thermodynamic arrows, biological clocks, and conscious experience. But none of that cancels the first insight. All those layers of explanation are different ways of saying the universe is never exactly the same from one now to the next, and you are riding that difference. You don't need to hold all the details in your head. You can let them blur together, like stars on the edge of your vision when you're too tired to focus. What remains is a feeling that you are embedded in something vast, lawful, and ongoing. You are not outside of time, inspecting it from a distance. You are a pattern that time is making, for a while, on the canvas of space-time. And now, it's time to rest inside that pattern. Let the pace slow. You notice how long each breath feels when you really pay attention. Inhale, cool air brushing the inside of your nostrils. Pause. Exhale, a warmer stream leaving your body, carrying a little bit of you back into the room. Each breath is a small wave on a much larger ocean of processes. Heartbeats nested inside minutes, minutes inside hours, hours inside the turning of the Earth, that turning inside its orbit, that orbit inside the galaxy's slow rotation, all of it within the expansion of the universe. With your eyes closed, time softens. The sharp edges between before and after blur into a gentle gradient. You are not at the Big Bang, not at the end of all things, just somewhere in the middle, like a leaf floating midway down a long river that began upstream in misty mountains you can only imagine. The science can fade now, like a lecture ending, and the lights dimming in a planetarium. You can keep only the images. A fabric of space-time, curved by stars, cradling your world. Tiny quantum ripples, stretched into the web of galaxies. A faint fossil glow, still streaming through your room from the universe's childhood. An arrow of entropy, drawing a line from cosmic simplicity to intricate complexity right through your life. Your own heartbeat and breath. Small clocks nested inside the big one. As you sink deeper into the mattress, let those images drift apart, like dandelion seeds on a slow breeze. You don't have to understand how time began to be soothed by the fact that, right now, it is carrying you gently forward, second by second, toward rest. If worries about tomorrow try to crowd in, you can remind yourself, tomorrow doesn't exist yet, not as an experience. It's a possibility, not a place you have to stand in tonight. The past is already woven into your world line. The future is still loose thread. The only part you have to inhabit is this soft, expanding now, where your body is safe and the universe is doing what it has always done, unfolding. Feel the weight of the blanket as a kind of local gravity, drawing you inward instead of outward. Hear whatever faint sounds there are, distant traffic, a fan, the whisper of air, as tiny fluctuations on an otherwise calm background, like the cosmic microwave background smoothed across the sky. Everything is quieter than it was at the beginning of the universe, and quieter than it will be in your most active hours tomorrow. You've walked a long path in thought tonight, from the first fractions of a second after the Big Bang to the private seconds before your sleep. You've seen that the beginning of time is not a single simple answer but a frontier, where our best theories meet uncertainty, where timeless equations may give birth to flowing time, where questions might be more fundamental than any single reply. And yet, here in this room, the mystery becomes very simple. Time is the softness pressing against your skin, the cooling of the air, the slowing of your thoughts. It is the way this sentence ends, and the next begins a little more slowly, and then stops. The universe has been here for billions of years. It will be here after this video ends, after tonight ends, after many, many other nights. You are allowed to put the question of beginnings down for a while. You are allowed to float. Let your breath be the only clock you care about. In and out. In and out. The universe is still here, quietly working while you sleep. And you, tiny and finite and irreplaceable, are free, now, to rest inside its ongoing river of time.